Right, so maybe before we start talking about the coordinate systems, let's talk about la différentielle. And I know that is going to, help us. I'm not going to then maybe we'll talk about le déplacement élémentaire, but then we'll talk more about these concepts a little later when we talk about the coordinate system. So I'm going to shift to the board, and of course, if there's anything, please don't hesitate to inform me. In case we have any problems, the screen disappears or you stop hearing what I'm saying. Bien. So let's look at la différentielle. La différentielle, remember, in mécanique du point matériel, we'll be talking about, differentiation, a lot of differentiation and all that good stuff. So we have to understand that we'll position ourselves in a 3D space where every vector is going to have how many components? It's going to have 3 components. So we'll position ourselves in a 3D space where every vector is going to have 3 components. So let's say we have a vector V that has 3 components, that is X, Y, and Z. Then la différentielle de V is basically going to be equal to la dérivée partielle. Remember that V has 3 components, X, Y, and Z. So it is written en fonction de X, Y, et Z. So if you want to differentiate such a function, all you have to do is you first of all differentiate it with respect to X, and then we differentiate it with respect to Y, and then we differentiate it with respect to Z, and then when we take the sum, we're going to have la différentielle. So la différentielle, c'est la dérivée partielle de V that has 3 components, X, Y, and Z, like so, par rapport à X, like so, and then plus la dérivée partielle de V, so that has 3 components, X, Y, and Z, like so, par rapport à Y, and then plus la dérivée partielle de V that depends on 3 components, X, Y, and Z, par rapport à Z. Now, this quantity dV, and of course, we have to multiply here by dx, here by dy, and then here by dz. Now, this quantity here is what is known as la différentielle de V. La différentielle du vecteur V. La différentielle. Voilà. So, this is la différentielle. So, it is dV. C'est la dérivée partielle de V par rapport à X, plus la dérivée partielle de V par rapport à Y, and then la dérivée partielle de V par rapport à Z. C'est bon? So this is what we have here. So with this dérivée partielle, we can now talk about le déplacement élémentaire in the Cartesian coordinate system. Now we'll see, we'll make a few modifications here, to see what is going to happen. But then let's now first of all talk about the Cartesian coordinate system. Then we can get back to this expression and see how this is going to sort of give us an expression of what is known as le déplacement élémentaire. Le déplacement élémentaire. So the Cartesian coordinate system, c'est très très important because we'll be talking about reference frames. If we want to talk about the velocity, if we want to talk about the position of some particle or some point M in space, we'll be talking about these coordinate systems, the Cartesian coordinate system and the cylindrical coordinate system and the polar coordinate system. So we'll first of all we'll talk about the Cartesian coordinate system, and to save time, we'll just talk about the Cartesian coordinate system and the cylindrical coordinate system, and also about the polar system. And then when we find a question that has a question where we have the spherical coordinate system, then we'll talk about the spherical coordinate system there and then solve the exercise, right? So we'll save a bit of time. Let's talk about the Cartesian coordinate system. So for the Cartesian coordinate system, well, just like I told you, we have three axes. So we have the x-axis, the y-axis, and the z-axis, like so. So now this is going to be my Cartesian coordinate system. So this is going to be the z-axis. By the way, this is the positive z-axis, and then this is the positive y-axis, and then this is the positive x-axis. Now sometimes other people like to write y here, and then they write x here. So it's the same thing. C'est exactement la même chose. Then the unit direction of vector. The unit direction of vector along this, along the y-axis is known as j. like so. Or we're going to call it, in this case, we're going to call it EY. So EY, like so. This is the unit directional vector along the y-axis. The unit directional vector along the x-axis is going to have EX. C'est bon? And then the unit directional vector along the y-axis is going to be EZ. EZ. Now, other people would also say, you also find things like this. EZ. This EZ can be K for some people, and then others will represent it as UK. Like so. C'est exactement la même chose. Même chose. EY. Other people will represent it as, other people will write it as, bon, c'est pas mal. So, G, like so. And then UY. And then, like so. And then this EZ, other people will write it as what? Will write it as, bon, EX, because EZ I've already written it on top there. So other people will write this EX as I, like so. C'est bon? And then they also write it as, by example, UX. Okay? So you also find, things like this. You also find things like this. Now, this is what is known as an orthonormal basis. So orthonormal basis. Orthonormal basis. Now, what this, so let me just, and then this is my origin. Let my origin, this all is going to be my origin, like so. So the vectors EX, EY, and EZ form what is known as an orthonormal basis. So this is known as an orthonormal basis. So what does orthonormal mean? So let me just, orthonormal basis. So we will talk about, les espaces vectoriels in algebra later on. You're going to understand what a basis is, or une base. We're going to talk about these things a little later. But then what orthonormal means in this case? Orthonormal means two things. So orthonormal in this case means orthogonal. By orthogonal, we are saying that if I take any two of these vectors, they are going to be perpendicular to each other, meaning EX is perpendicular to EZ, and then EZ is perpendicular to EY, and then EX is also perpendicular to EY. Take any two of these vectors, they are going to be perpendicular to each other. That's what orthogonal means. And then it means, orthonormal means orthogonal plus normalized. Normalized. By normalized, we are saying that EX, EY, and EZ, they are of unit length. They are of unit length. So in simpler terms, orthogonal means perpendicular. Perpendicular. Sure, we are familiar with the word perpendicular. And then this normalized means that the vectors are of unit length. C'est bon? Je passe? Est-ce que c'est bon? Je passe?
Yes, you can pass.
Très bien. So this is the Cartesian coordinate system. Okay? This is the Cartesian coordinate system. So it is the vector EX, EY, EZ form an orthonormal basis. Now, orthonormal means two things. It means orthogonal. Orthogonal meaning take any two of these vectors in whatever combination. EX, EY, EX, EZ, EZ, EY. C'est pas mal. So you can take any combination you want. They're going to be perpendicular to each other. Deux à deux. And then the other part is that they're going to be normalized, meaning the vectors are going to be of unit length. C'est bon? So, and then if I take EX dot, if I take EX dot EY, I'm going to get 1. If I take, I'm going to get 0. I'm going to get 0. Who can just, why am I getting 0 here? Well, it's because if I take, is that a question?
No.
Okay. C'est bon. Let me just maybe see what is happening here. Ça va, c'est bon. Okay. So if I take EX dot EX, I'm going to have 1. I'm going to have 1. Now EY. If I take EY, I'm going to have 1. La même chose. EZ dot EZ, I'm going to have 1. But if I say EX dot EY, because it's an orthonormal basis, there's this orthogonal part here, this is going to be 0 because EX and EY are perpendicular. And if two vectors are perpendicular, the dot product is going to be equal to what? It's going to be equal to 0. So you can also have the other combinations here. You can continue with the other combinations here. But then I'm going to summarize here. I'm going to say that if we have EI dot EJ, like so, this is going to be equal to what is known as the Kronecker symbol. So it is delta IJ, like so. Now this is defined by, the result is going to be 1 si I est égal à J. It is going to be 0 if C, it is 0, 0 sinon. So we can just say 0 sinon, like so. So what does this mean? So if I is equal to J, if I have EX, I'm going to get 1. If I say EX, EY, here I is different from J, so I'm going to get 0. If I say EX, EY, I see that I is equal to J, and so it gives me 1. So this is what I've written here. This is the same thing. This is the same thing. This is what I've written here. Est-ce que c'est bon? Ça va? Je passe? So EI.EJ is the Kronecker symbol. So this is known as the Kronecker symbol. Kronecker symbol, like so. Kronecker. Sure, it's something like this. The Kronecker symbol. And then it is 1 CI is equal to J, and then it is 0 sinon. So this is what we have. Then another piece of information is le déplacement élémentaire. Le déplacement élémentaire, c'est, let's say we have, let's say we have a point M that's here. So it's important to talk about the position or coordinates. So let's say we have a point M that is here. So what we do is that we draw a line from the origin to the point M. So let's say the point M is here. Sorry, it's a point, not a vector. So let me just correct what I've written here. Let's say we have a point M somewhere here. Let's say we have a point M here. So the first thing that we want to do is to draw a line from the origin to this part here. And then the position of vector OM here is going to be given by what? In the x-axis. I mean, it's going to be given by, since we are in a 3D space, there will be an x part. There will be a part that is going to have x. Then there will be a part that is going to have y. There will be a part that is going to have what? Z. C'est ça. C'est le vector position. We call it vector position, or the position of vector. It is x, EX, like so, plus y, EY, plus z, EZ. So this is what we have. C'est OM. C'est ça. Voilà. So this is the position of vector. So any vector in space is going to have this representation. Any vector in space is going to have this representation. It is going to have x, y, z, and then so we have EX, EY, EZ. C'est bon? So let's take a few examples here. Let's say I have a point here. What is the position of a point that is somewhere here? So let's take a point here. Let's call it by simple math. You can take whatever you want. Let's use P. So let's say we have this point P that is here. So what is the position of vector OP? Normalement, we have to draw a line from the origin to the point P. So we should have OP here is going to be equal to what? OP is going to be equal to say X. Normalement here, because P is on the y-axis, the value for X is 0. The value for X on the y-axis is 0. Rappel. So 0 EX, 0 EX, and then plus on the y-axis, so, but we don't know the length here, so we just say y, like so, EY, and then plus, what is the value for Z? The value for Z on the y-axis, so 0. So you put 0, and then EZ, like so. Now finally, the vector OP here is going to be equal to Y, EY. En general, this is the formula that gives us the position of any point in space. Je passe? C'est bon? Je passe?
Oui.
Très bien. So, one last thing about bien. One last thing about now these unit vectors EX, EY, and EZ are constant. Now what do I mean by, say, What do I mean? I mean, if I take the derivative, la dérivée par rapport au temps, they are constant, hein? They are constant with respect to time. If I differentiate EX par rapport au temps in a reference frame R, so a reference frame is, I have this base here, un référentiel. R, for example, if I call this reference frame R, the origin here is O, right? So I have to specify the origin and then the base. So this is what makes up the référentiel. EX, EY, and then EZ. And then we add the time dimension. If we add the time dimension, we'll have a reference frame. The difference between a repère and a reference and a référentiel is that a repère is, to simplify things, is without the time dimension. But for a référentiel, we're talking about, we add the time dimension. So that's why here I'm saying the derivative of EX with respect to time is equal to the derivative of EY with respect to time in the reference frame R, which is also equal to the derivative of EZ with respect to time in the reference frame R is going to be equal to 0. They are constant. So as time changes, they stay the same. They stay the same. Okay? They stay the same. As time changes, these vectors are going to stay the same. They don't change par rapport au temps. So when we have such a representation, we have what is known as a référentiel because we've added the time dimension. C'est O. It is O. L'origine, c'est quoi? C'est O. EX, EY et EZ, c'est la base. C'est la base. It is an orthonormal base. Orthonormal means orthogonal and normalized. Orthogonal meaning 2 à 2, the vectors are going to be perpendicular and then they are of unit length. Est-ce que c'est bon? Je passe? Je passe? Très bien. Le déplacement élémentaire, I think that this is, the last thing we'll talk about here on, Cartesian coordinate system. Le déplacement élémentaire, c'est simple. I won't talk about, where the formula is coming from and all that. So c'est pas l'objectif, c'est pas l'objectif. L'objectif, c'est we'll employ these formulas or these methods later on. For now, let's just have it as information. Le déplacement élémentaire, c'est 2x, EX, c'est 2y, EY, plus 2z, EZ. This is le déplacement élémentaire. So this is, for now, this is all about the Cartesian coordinate system. A few important points to remember is this product, the dot product here, the Kronecker symbol. And if you cannot, write it in this way, and then this is the very long way, a very long way of writing this. And then the different notations that you see when you maybe read different books or you see other notes, this is what you see. And then the other idea is that EX, EY, and EZ are going to form an orthonormal basis. Orthonormal means orthogonal plus normalized. And then a référentiel, we add the time dimension here. Then we are saying that EX, EY, and EZ are constant par rapport au temps. Meaning, if I take the derivative par rapport à t, I'm going to see that the derivative is going to be equal to 0. They are fixed. They are fixed. And then le déplacement élémentaire, c'est 2x, EX, plus 2y, EY, plus 2z, EZ. I move to another coordinate system, which is the cylindrical coordinate system. Bien, the cylindrical coordinate system, c'est simple. Now, I know you are familiar with what is known as the polar coordinate system, but I'm going to start, from the, c'est pas mal, the Cartesian, the cylindrical coordinate system, et puis I'm going to move to something else. Bien. So let's talk about the cylindrical coordinate system. Now, let me just add a new page here. Nouvelle page. Très bien. Hop. Like so. Now, the cylindrical coordinate system, même chose, we will be in a 3D space. Now, let me just allow myself here to choose a line. So let's say this is that axis, and then here I have this, and then here I have something like this. And let's just be consistent here. Our x-axis will be this, the positive x-axis, and then this is the positive y-axis, and then this is the positive z-axis. Now, let's say we have a point M in space here. We have a point M in space, like so. So for the cylindrical coordinate systems here, the bars here is going to be formed by 3 vectors, just like in the Cartesian coordinate system. So here the bars here is going to be rho. We'll see what rho is. We have rho, and then we have the angle. We have the angle phi, and then we have z. So this is also an orthonormal basis. So this is also a bars, just like the one we had in this. For the cylindrical, for the Cartesian coordinate system, we have Ex, Ey, Ez. For this one, we have rho. We have sorry, this is not a bars. Like the 3 pieces of information. In the Cartesian coordinate system, we have x, y, and z, right? Here we have rho, phi, and z. Okay, so if you can sort of like compare the two. In the Cartesian coordinate system, we have x, y, z. Here we have rho, phi, and ez. And then for the bars here, the bars here is rho, like so, phi, and then z. So this is a bars. So this is our bars, like so. So let's say we have a point M in space. If we have a point M in space, now the first thing that you want to do is to draw a line. So this is the origin. The first thing that you want to do is to draw a line from the origin to the point M. Now let me just use a different color here. So you draw a line from the origin to this point M, like so. The next thing that you want to do is to project this point M in the x or y plane. Now the x or y plane in this case is below. X or y plane is below. So we're going to project this vector. So to project a vector, we sort of like drop it down, we bring it down. Okay. So how do we bring a vector down? It's a sample. So we go dot. I'll just put dots here to show that I'm projecting this vector. So up here, and then I'll draw a line here. And then I'll put it maybe in a different color so that we see what is happening here. So this line here, I'm just going to call this small m, this point here. So this OM here is the projection, or small m is the projection of this point OM in the x or y plane. So I've projected. And then this angle here, I'm going to call it phi, like so. This angle here, I'm going to call it phi, like so. And then let's now represent the rho is here. Rho is this distance. It is the projection OM. It is the projection of this point M in the x or y plane. Rho is OM. Rho is OM. Je répète. Rho is OM. C'est bon? So this is rho, like so. So it is OM. The projection of this point M in the x or y plane is rho. Okay? And then the unit vector in this direction. The unit vector in this direction, maybe let's use a different color here. What color? Let's use yellow for instance. Yellow is a bad option. So let's choose a different color. C'est pas mal. So black, for example. So the unit vector in this direction, is euro. It's parallel to rho, so it's euro. So I'm just going to say euro, like so. This is the unit vector, and then the unit vector here, that phi increases in this direction. So when we are here, phi is 0, but it keeps increasing until we reach this point. Let me maybe use a pointer so that you see what I'm talking about. Here, phi is 0 here. Phi is 0 somewhere here. It's 0 somewhere here. But then as we go, it increases in this direction. It goes from 0 to until we go around until we arrive at 200. At 2 pi radians, or 360 degrees, as we all know, right? So the unit vector that is in the direction in which this phi is increasing is known as phi. This is where phi is. And then finally, Ez is the same vector. Ez is the same. It's parallel to the z-axis. So it comes here, then it goes like so, and then this is EZ, like so. So this EZ, EPhi, Euro are going to form a basis, an orthonormal basis, just like EX, EY, and EZ form a basis in the Cartesian coordinate system. Here they're going to also form what? They are going to form a what? They are going to form an orthonormal basis. So rho is in what direction? It follows, it's in the direction of this rho, this OM, this vector OM. And then phi is in the increasing it's in the increasing direction of this angle phi. The angle phi increases in this direction. Okay, it increases in this direction. So the phi is going to point in the same direction. EZ is going to be parallel to the z-axis. EZ, we can see it goes up, and then the z-axis is also going up. It's the same EZ that we have in the Cartesian coordinate system, but here we've replaced EY with phi, and then EX with Euro. C'est bon? Est-ce que je passe? Is everything okay? Ladies and gentlemen, je passe?
I didn't get the direction for
EZ.
what
Bien.
yeah.
So EZ is the same as it's the same EZ that we have in the Cartesian coordinate system. So it's parallel to the z-axis. So you can see. Let me just maybe use a pointer here to up. So look, this is the direction of EZ. It's going up. Same. The Z here, the EZ here. Let me also maybe draw the EZ here so that you see that we're talking about the same thing here. Up. So here, so this is the EZ. It's the same. So this EZ, you can put it here and put it here. Okay, but I just want to represent all the three, the three unit directional vectors. I want to write them on the same place. Put them in the same place. So that's why the EZ I've put it here. But it's the same EZ that is here. They are parallel. Is it okay? Ça va?
Yeah, so like this over it's like the projection of the pointer from the projectoire of the pointer.
I'm not sure I get your question. Repeat.
We have the point M there on top.
Yes.
Medium.
Yes.
Then we have projected M.
Yeah, we projected M
Now
in the X or Y plane. So it's that's why I put a small M here at the bottom.
yes, and then now you've come with this direction for I don't know if the vectors for UZ over what's this? I don't know. Yeah, they are
Phi.
these vectors that are here present the direction. I don't know if the direction of M, the small the projected M.
Yeah, so the first thing that we did is we projected M in the X or Y plane. So in the Cartesian coordinate system, we have a base. We have EX, EY, and EZ. Now those are on the axes X, Y, and Z. Here for the cylindrical coordinate system, here it's different. We have a new parameter theta that has been introduced here. And then when we project here, we will have a point M here. That is all the down, vertically downwards here. It's vertically downwards. From M, it goes vertically downwards. We arrive at M. Then the distance OM here is rho. The distance here OM is rho. It is the length, it is the distance here of this projection of OM in the X or Y plane. So we project it here, we project it in the X or Y plane. And then the direction of rho is going to be the direction of this vector OM is going to be rho is going to be in the direction of the vector OM. And then phi is going to be in the direction of the increasing phi. Okay, because phi increases from this point here. Here it's 0. Here it's 0, but then it increases. Here it's 0, but then it increases going this way. So phi is going to point in that direction. And then EZ points in the direction of the positive z-axis. So that is what you are supposed to remember. You project the point, forms an angle with the x-axis. Rho points in the direction of the vector OM, or O small m. And then phi points in the direction of increasing phi. And then EZ points in the direction of the z-axis. Ça va?
Yeah.
Très bien. So now let's talk about the position vector. Just like we wrote the position vector for the Cartesian coordinate system here. If I want to go to OM, I cannot go directly to OM using this line in red that I've drawn here. I have to pass by this OM because I want to make use of this rho that I have here. I want to make use of this rho that I have here. C'est bon? Yeah, I want to make use of this rho that I have here. So I can say OM is going to be equal to the vector O, and then I can pass through this OM. If you remember your vector lessons in grade 12, if you cannot go directly from O to this big M, you can go O small m and then small m m. So plus small m m, like so. So this is the direction we're going to follow. Okay. Now we know that OM here is rho. OM is rho, but it's a vector, so you have to also indicate the unit vector. The unit vector in this case is rho. In the direction of rho. The unit vector in the direction of rho is rho. So we have rho, and then we're going to have rho, like so. Okay. And then plus, well, this line here from the bottom to the top here, we can just say, okay, it is at a distance z. It is at a distance z. It is at a distance z. So here we can just say z and then z, like so. We can just say, okay, this vertical distance here is z. It can be anything, but in this case, we just say, okay, it's z, because we don't know, we can't put a specific value here. So we can just say, okay, it's at a distance, the length of this vertical line here is z. And so we'll have z, z. Okay, z, z. So z is a vector, so we z is like the number, the length, the magnitude. But then z here adds direction, adds another characteristic to this, to this quantity to make it a vector. So I repeat, je répète. So to go from O to M, we go from O to small m and then small m to m. So it is going to be, this OM here is rho. And then you write the unit vector in the direction of rho, which is a rho, plus here we say, okay, the distance of this, the length of the magnitude of this vertical line here is z, and then it is in what direction? It is in the direction z, just like I have indicated here. So that's why we have z. So this is what is known as the position vector, le vecteur position, le vecteur position, le vecteur position. And then rho is in the interval. Rho is in the interval 0, positive infinity. So it can be 0, rho can be 0. For example, if the point M is taken on the z-axis. If the point M is taken on the z-axis, then rho will be 0, right? Because if I project it in the x or y plane, it's going to be downwards, somewhere down here, but close, very close, coming to at the origin here. So rho is going to be in the interval. Rho is going to be in the interval 0, positive infinity. Then we open the interval on the side of positive infinity, because positive infinity is not a number. And then phi here can go from 0 maximum to pi, like so. And then z here can be, remember that here we have the negative z-axis and the positive z-axis. What I've just shown here to simplify things for us is the positive z-axis. However, we can also have the negative z-axis. If I continue down here, it's going to be the negative z-axis. So we are moving from minus infinity to positive infinity, like so. So this is the interval for z. Rho can be any number between 0 and positive infinity. Phi can be any angle between 0 and 2 pi. Then z can be any number from minus infinity and positive infinity, because we have the positive z-axis and the negative z-axis. Okay, c'est bon?
Oui, c'est bon.
Très bien. And then there's a correspondence between the Cartesian coordinate system. You can move from if you have the Cartesian coordinates, there's like, we have parametric equations that sort of like link the two coordinate systems. So we have parametric equations that link the two coordinate systems. So we have this x here. The x coordinate in the Cartesian coordinate system is linked to So x in this case, so this is Cartesian. So link between the Cartesian and cylindrical coordinate system. So this is like a link, right? So link. So these are known as parametric equations. Parametric equations. So how do you come up with these parametric equations? It's a sample. So look, here we have this angle here. Let me just get rid of this. Up. So what I'm going to do is, I want to project. There's this projection of this point M in there's this projection of the point M in the x or y plane. Here where there's small m. So we have this one. So what we're going to do is, I'm going to sort of like draw a triangle here. I'm going to like complete the triangle here, such that here I have 90 degrees, like so. So you have a triangle like this. Let me just represent it here. So here you have a triangle like this. You have a triangle like this. So if you remember your SOHCAHTOA, very well, this is where our angle phi is, like so. And then this is the x-axis. This is the x-axis. And then this is the y-axis. If you remember your SOHCAHTOA very well, you see that we have SO and ka. So we have SOHCAHTOA. So let me just say SOHCAHTOA, like so. So we know that sine phi is going to be equal to the opposite divided by the hypotenuse, and then cosine phi is going to be equal to the adjacent divided by the hypotenuse, and then tan phi is going to be equal to what? It is going to be equal to the opposite divided by the adjacent, like so. So here what we want to do is to project, to carry out projections, to project this vector, this hypotenuse that we have here. If we want to project it on the x-axis here, so this is my opposite, right? This side here is the opposite side. This side here is the adjacent. Then this side here is the hypotenuse. So here, this side here, the side that has here opposite here is going to carry sine of this angle. And then the side here, which is the adjacent, is always going to carry cosine. Sine, this is going to carry sine, this is going to carry cosine. So this is the opposite here. So this side is going to carry sine. Then this side is the adjacent, is going to carry a cos. Okay? So we have, and so here if you project here, and then times the hypotenuse, right? Or if you are lost here, let's use SOHCAHTOA. Let's use SOHCAHTOA here. Let's apply SOHCAHTOA. If you apply SOHCAHTOA here, our hypotenuse here has length rho. Our hypotenuse here, if you look at what we have here, our hypotenuse here is rho. C'est bon? And then here, we don't know the length of this side here. So we just say y. Because, yeah, we'll just say y. Because this side is parallel to the y-axis. It's this side here that is parallel to the y-axis. Let me maybe use a pointer so that you see the side I'm talking about. This side here is this side. Okay? I've just drawn the triangle in a way that you can sort of like see what is happening here. Okay? So, our hypotenuse is rho. And then here, along the x-axis, along the x here, let me just get rid of the SOHCAHTOA here. I'm sure you remember these things. So let me get rid of that. And then here, because we don't know the length of this side here, we'll just call it x. Okay? We'll just call it x like so. Then what is sine? So sine phi. What is our opposite? Our opposite is y. The hypotenuse is what? Is rho. Okay? And then what is our cosine? Our cosine phi is what? What is the adjacent? It is x. What is the hypotenuse? It is rho. Okay? So let's now make x and y a subject. So here if you make x a subject, you get x is equal to what? X is equal to rho. And then you have cosine phi. And then y will be equal to rho sine phi. And then z here is going to be equal to 0. Why is z equal to 0? It's because we are in the x or y plane. In the x or y plane, the value for z is 0. In the x or y plane, z here will be equal to z. Z will be equal to z, sorry. Not 0, but z will be equal to z. It's a mistake, okay. So z will be equal to what? z will be equal to z. So in the cylindrical coordinate system, these are the parametric equations that sort of like link the Cartesian and the cylindrical coordinate system. Now when z is equal to 0, we have what is known as the polar coordinate system. Okay, we just use the polar coordinate system because we don't have the part for z, so we just use the polar coordinate system. Okay, c'est bon? So these are the parametric equations that link the two coordinate systems, the Cartesian coordinate system and the cylindrical coordinate system. C'est bon? Are we following? Okay. Are we following?
For me, it's okay.
Très bien. Okay. So this is what we have. Now, another equation, important equations you're supposed to remember is, now due to time, I'll just write these things, but just use the same concept for, projecting and all that. Just use the same concept for projecting. I'll give you, I'll leave it to you to do the projections and then confirm that euro, this unit vector euro, is going to be equal to cosine phi ex. If you fail, if you don't arrive at this, answer, you can just let me know so that next time we start from here. Okay, but finally, let me just write. So euro is going to be equal to cosine phi ex due to time, and then sine phi y, like so, and then phi is going to be equal to these. You must know them by heart. You must know them by heart. Okay, sine phi ex, it's minus here, and then plus cosine phi. If you, to make life easy, you can sort of like get rid of the z-axis. Get rid of this z-axis that I have here. Get rid of this z-axis. Euro is in this direction. Get rid of this z-axis and then draw a simple system. A simple two-dimensional system that you can use to find these answers. So for now, I'll just write them, and then you're going to remember them. And next time, if you don't understand what I've written here, we can start from there. But now, let me just save, optimize. So this is that, and then I remember I told you that the EZ in the cylindrical coordinate system is the same as the EZ in the Cartesian coordinate system. So euro is in the cylindrical coordinate system, Ex and Ey are in the Cartesian coordinate system, Phi is in the cylindrical coordinate system, but Ex and Ey are in the Cartesian coordinate system, and then Ez is the same as Ez. Okay, so I'm just saving a little bit on so that we don't lose a lot of time. And then other important pieces. These things you must know them by heart. Must know them by heart. Must know them by heart. Then the derivative of euro with respect to phi. The derivative of euro with respect to phi. The derivative of euro with respect to phi. When you differentiate this, you can try. Just look at these equations. Look at these equations that I've written here. And you should be able to get, if you differentiate euro with respect to phi, what are you going to get? You get phi, like so. And then if you differentiate phi with respect to phi, you're going to get moins. You're going to get moins euro, like so. How do you differentiate here? You have a sum here. The differentiation or the differentiation operator here is distributive. So you differentiate, when you differentiate cos, you get minus sign. You differentiate cos, you get minus sign. So here we have two functions. We have Ex and cosine phi. Remember that I said that the derivative of Ex, the derivative of Ex is just when you differentiate this cos, you get minus sign. Then you differentiate the sign here, you get cos, like so. The derivative of cos is minus sign. The derivative of sign here is cos, and then you see that you get phi. You differentiate phi, this one, with respect to phi. Let's see, you differentiate sine, you get cos. You differentiate this cos, you get minus sine. You factorize by the negative. This is the minus that we have here, or the negative one. This is the minus that we have here. And then what will be inside is the rho. So these things, you have to know them by heart. You have to know them by heart. Très, très important. You have to know them by heart. These two things. This part and this part must be known by heart. You must remember these things by heart. Bien. And then another thing is, another thing that I'll just write immédiatement or directement is le déplacement élémentaire. Now, if you're interested in the formal, derivation, how we can derive this déplacement élémentaire, we can look at it later on, but this is not the objective. So let me just write. So here you have d rho, d rho, and then you have euro, like so, and then rho, and then d phi, and then phi, and then plus dz, ez. So this is the déplacement élémentaire. So what we did for the Cartesian coordinate system, we've done for the cylindrical coordinate system. Okay, what we did for the Cartesian coordinate system, we've done for the cylindrical coordinate system. Now we'll look at the spherical coordinate system a little later. For the polar coordinate system, it's for the polar coordinate system, it's when z is equal to 0 for the cylindrical coordinate system. So we will just use the polar coordinate system in that particular case. Okay, so we'll look at the spherical coordinate system a little later, because most of the questions are going to be about the cylindrical coordinate system and the Cartesian coordinate system. When we find a question on the spherical coordinate system, we'll look at it, because we're a bit late, so we have to sort of like move a little bit faster so that we can cover many things at the end of the day. C'est bon? Cylindrical coordinate system, Cartesian coordinate system, ça va? Cylindrical and Cartesian. Is that a question? Okay, ask your question.
When you differentiate those two vectors, are they supposed to be perpendicular to each other?
What vectors? Rho, phi, ez? Yes. They form a basis. They form an orthonormal basis, just like in the Cartesian coordinate system, they form an orthonormal basis. So meaning they are perpendicular, deux à deux, and then they are of unit length.
Okay.
Right. And then maybe one thing that you're supposed to know is this circle. Let me just, I know that I have under 11 minutes, but so let me just, this circle that we have here, or maybe simple mal, we cannot draw the circle. So we have rho, phi, ez. This is the direction you must follow when you're taking the vector product. So if I say rho vectoriel phi, in this direction, this is the positive direction, rho vectoriel phi, this is going to give me ez, like so. And then if I say phi vectoriel ez, I'm going to have rho, like so. But if I go in the other direction, if I say, for example, phi vectoriel rho, is going to be minus the other one, which is minus ez. So if I to have positive here, I must follow them in this direction. So rho, phi, ez. But if I go phi rho, I'm going to have a minus ez. And then if I go ez vectoriel phi, I'm going to have minus euro. So this is another interesting thing. We'll be using this a lot. So I suggest that you remember this part here. Is this part clear?
Can you repeat on the going back?
Okay, when going back you get negative. The positive sense is going forward. Euro, EFI, EZ. You get the other one, but you get positive of that other one if you go in this direction. But if you say EZ, EFI, EZ vectoriel, EFI, it is going to be euro, but you put a negative because we are opposing the conventional positive direction. You understand?
What if I get the first one and the last one?
The first one and the last one, you're still respecting the direction. It is, if you say euro vectoriel EZ, it is positive EFI because you're still respecting the direction. You get the first one and then the last one. Huh? So you're still respecting the direction. C'est bon?
Mm-hmm.
Right. Now I can see that we have under 8 minutes here. So what we can do is we can come back for maybe let's say 30 minutes so that we define velocity and all that good stuff, how to represent velocity in the Cartesian coordinate system and the cylindrical coordinate system. Then we can maybe see how we can over the weekend solve a few exercises on these things, and so that we complete everything. So we'll exit this one and then we'll come back for 30 minutes or so. So we can exit this one.